This is the second in a series of videos in which I am trying to create a drop-in replacement for the tape drive on a Fluke 9010A microsystem troubleshooter. The idea here is to make a small circuit that fits in place of the cassette, plugs into the same port on the main unit, but gives us a solid state storage solution rather than using tapes. So in the first video in this series I introduced the basic project and what I was going to be doing, and I said there were various options I had for going about this. So if we look at the schematic, I'll just briefly recap on what I said in the first video, in that we could either make a unit to plug in place of the actual cassette mechanism, or we could replace the mechanism and the kind of analog interface section, which is the main part of this board and the mechanism, or we could replace the entire thing and have our solution plugging in to the port. In other words, we'd replace the entire thing, everything that's connected to this ribbon cable. And that's what I've decided to do. I'm going to replace the entire mechanism. I'm not going to retain this device. If you're not familiar with these are Intel 8041 devices. They're akin to a fairly old microchip PIC in that they are self-contained microcontrollers. They've got built-in mask ROM or EEPROM and built-in RAM and a microprocessor core and various peripheral interfaces. So what we're going to do is replace all this, and that device is this one, and it contains some code. And at the end of the last video I said I was going to look at this code. I'd already taken it and disassembled it. The code I disassembled wasn't actually from this machine, it's code I found online. And the plan was I was going to go through and disassemble this, annotate it, and figure out exactly how the code was structured. And that would give me a good starting point to decide how to go about recreating what I needed in a microcontroller. A lot of it I won't need, of course. I won't need to control the hardware, but I will need to respond to the 9010A as if though the hardware's there. So if it's looking for example, certain things, rewind, so hitting the end of the tape, tape present sensor, that sort of thing. That's all done within this device, but it is a requirement for the 9010A that this device reports back that it's happy with the tape, etc., or that it's found a particular program. So we will need to reproduce all that, and the easiest way to do that is to look at the code that's running in this device, and then in conjunction with the schematic we can figure out what each particular port is controlling and what each pin's doing. So firstly I figured out what each pin is connected to, so how this is working in terms of controlling the motor, the solenoid and the read-write head. I then started going through the code. So if we start at the beginning, the reset vector for this device is 0, and in fact the first few bytes are reset vectors for various things, or interrupt vectors, so for the interrupt, the timer, that sort of thing. So I was a bit concerned when I first started reading through this. You get a feel fairly quickly when you do this a lot as to whether the code looks right or not. And this didn't really look quite right, but I started following it through. So the first instruction, this is decompiled using a fairly common disassembler that you can download, run it through this, and the first instruction decoded as a jump, which makes sense, that's what you'd normally expect to see, and it jumps to address 31. So if we went down to 31, I started going through this. The first instruction was clear accumulator, it makes perfect sense, and then it started doing what appears to be various initialization, so writing values to the various ports. So that's essentially configuring and resetting all the hardware on the cassette drive, and that again makes sense. It's done by this device after a reset. It's not done by commands sent directly from the 9010. The problem, however, is I got down to this instruction. It's all fine so far. I was even at this point checking that the actual instructions were being correctly disassembled. I hadn't used the disassembler on this particular device before, so I was seeing how good a job the disassembler was doing. The problem is when I got down to this instruction, or what should be an instruction, there's no jump out of here, so it has to complete this next instruction. But it's showing it as a data byte value of 22 hex. The value was correct. That's actually what's on the in the file, but it makes no sense. There's nothing. This code won't run like this. It'll get this far, then it would crash because it's not seeing it as an instruction. So I thought perhaps the file I'd downloaded was corrupt or just wrong, wasn't the right one. So I popped the device out of my actual cassette, and this cassette works, so I know this code's correct. So I popped this device out, put it into my reader, read it, and then ran it back through the disassembler. I got exactly the same thing. It was doing exactly the same disassembly. I was getting the same values and the same problems. There's no point me really going beyond that, because the code as it is being decompiled isn't going to run like this. And I found, just glancing through, various things that just do not look right as I was going through. So I started going through this, and I was looking at the data sheet for this device, and I was looking for the opcode 22, and it's not in here. So this is the data sheet for this particular device. So it's a UPD 8041, and there is no 22 in. However you look at it, so there's various options in terms of values for the opcodes, but there was not an opcode that matched 22. I started looking around at various, I've got other documents for these devices, and as I think I've mentioned in previous videos, there were various clones made of devices over the years back then, and one of the other suppliers, or the main supplier for this, was Intel, where they supplied it. Incidentally, thanks for the information that you sent through on this. There were various different instruction sets, and there is a particular instruction set for this. It's not an 8048 processor as such. It's got its own entirely separate set of commands, although it is a defined language. And that's what's defined in the main Intel data sheet. So I ditched this one, and then I started using the alternate one, which is this one. And in this one there is an opcode 22. So I started going through and using this as the source document to do the decompiling. I would say at this point that this device, like a PIC, the program code is banked, as is the memory. So just to make sure that wasn't causing any issue, I also tried decompiling it in separate banks. So each bank I tried decompiling separately, but I got exactly the same thing. So when I do it bank by bank, and I tried all different manner of settings, I even tried disassembling it using threading, and that wasn't really successful on this device. But either way, it always came up with the same problem here. We've got this file and it stopped, and that didn't matter whether I used independent banking or did it all as one combined file. So although it's not a particularly big program, I didn't really want to have to go through trying to figure out which of these commands were right and which were wrong. As you know, that can be very error prone, because it kind of depends on the error may be further back, and some commands may coincidentally appear to be correct and then fall on its face later on, and that can take a very long time to sort out. So what I generally do at this point is just write my own disassembler. It's I've probably written 20 or 30 over the last 15 to 20 years. It doesn't usually take very long. So I spent a couple of hours yesterday, wrote a disassembler. We'll have a quick look at that in a minute on the PC. When I run the same file through my new disassembler, what I end up with is this. So this is running through mine, and of course I've included all the commands that are in the main Intel datasheet. So what I did was take the data set, print that off, and then I've gone through and I've made sure that each of the commands that are in here, each of the instructions, are properly encoded within my disassembler. I've gone through every single one. There's quite a few instructions in this device, and of course a lot of them are sort of multi-option, multi-register. So it didn't take too long. It took me about 2 or 3 hours to write the disassembler. Ran the file through it, and what I'm now getting is this. I currently only have it written as a single pass disassembler, so there is no jump labels. I may do a small change to it and add multi-pass so it can create labels as to where it's going to jump to. You can't do it going just through a single pass, because if the jump is backwards, then you've already missed the opportunity to put your label in place. So when writing a multi-pass disassembler, then what you do is you run through it first, making a list of all the jump destinations, and what you can then do is replace all the jump addresses and the jump destination addresses with labels, and that makes it a lot more readable. But I haven't done that yet. It's quite easy to add, but because it's such a small program, I may not do that. I might just do this manually. There's only probably 20 or 30 jumps in here to different addresses. But what I end up with now is the same initial jump to the same address. So if we look down to the destination address, we can see that initially we're getting exactly the same thing. So it starts off with a clear accumulator, and then we get the same first few instructions. The difference is when we get down to instruction at address 38, which is still 22 because that's the value in the file, it now disassembles as in a DBB instruction, which is basically it's reading the interface byte from the controller. So that's the data coming down this cable, which of course makes perfect sense. It's one of the first things it wants to do, to see if there's any data for it to read. And then going through the rest of the code, it all seems to make far more sense. As I said, you get a good idea reading through something like this, just as a glance, as to whether it's right or not. In this, there was a lot of blocks of code that just suddenly turned into data bytes for no apparent reason, without any jumps preceding them, which meant the code would run to that point and then in theory it would crash if that's what it was trying to do. So this, I think there's a problem with the disassembler, and it won't disassemble this code correctly. I read through the documentation and it says it should disassemble this device, but it just doesn't work. So as I say, I wrote my own and it now seems to be doing what it should do. Also, I said the beginning on here didn't look right. This should be a lookup table, a vector table, so it should consist of pretty much nothing but jumps, and that's exactly what we get. On here you can see that each of the vectors is a jump to a specific destination. So these are the handlers. So for example, there'll be one of these, I can't remember which one it is, but one will be for the timer handler, reset, interrupt, that sort of thing. So we'll now know already what we're looking at when we look at the addresses at these locations. So I said I may go through and make this a second 2-pass disassembler. I do have a few other projects where this device will be used. The other one, of course, is in the keyboard and display project that I'm doing on this. So I may well put another hour or so in and turn this into a multi-pass disassembler. I might need to use it in the future anyway. But that's where I am with this. What we'll do now, just to finish off this video, is go and look at the PC. I'll give you a quick run through of how I wrote this disassembler. If it's something you've done yourself, then you'll find it fairly boring, but if you haven't seen a disassembler before, I'll give you a quick look at it. I won't go through it in a lot of detail, just a quick glance. And then the next step with the project is to go through. I will then annotate the code so that it's more readable. And then it will be a case of connecting the logic analyzer, and we'll start looking at the data coming into and out of the 8041 to see how that correlates with what we're seeing in the firmware. And what I can start doing then is taking this and turning it into a required functional flowchart that I can use to create a microcontroller. and obviously from that point on it will be very easy to finish off the project. So we'll go and look at the PC and have a look at the source code for the decompiler. Okay, we'll take a quick look at the Disassembler source code, and I'm using Rad Studio here, so it's written in C++, and started off with a very simple form. It just has a couple of edit boxes for either typing in file names or a couple of buttons to allow me to browse and select a file. So it's not a command line tool, it doesn't have a graphical interface. And then a button to start the process and a progress bar. And looking at the source code, it's all very straightforward, and for efficiency I tend to keep loops unraveled. You can roll a lot of what's in here up into loops, but it tends to slow it down. So all that's in here is when you select a file, the software creates a file handle to generate a stream for the file. It reads the entire input file into a buffer. I tend to find that's far more efficient with this sort of tool than reading byte by byte from the file, which is very slow. Also weigh your hard disk out as well. A bit of error checking to make sure it can generate the buffer. It then reads the entire file into the buffer, closes that file handle, then opens a second file handle to generate a stream for the output file, and it then uses the number of bytes it's read from the file that you selected to process as the progress bar indication, but also so it knows how to proceed and when it's finished. It then generates a line number, so this is done for each byte or pass, although some of the instructions are multi-byte, so I'll come back to that in a second. So the first thing it does is generates the line number at the beginning of the line. It also generates the characters for the end of the line, the new line characters, new line and character return. So it puts the number at the beginning of the line, it's in hex, and some separation characters just for formatting. It then reads the first byte of the next instruction and it prints that on the screen, or rather puts that into the file. And it then, there's a big switch now that just selects, it's looking for the match for the command that it's read. So the way that this disassembler works, based on the instruction set for this device, is each instruction, the first byte it reads will be unique. And that's what it's looking for. It's looking for a match for the byte value, which is this. When it finds it, it knows it's found the correct instruction. So the next thing it does is decide whether it needs to add some more formatting information. So that's whether it's a single byte or multi-byte instruction, just to make the output look a bit neater. And then it writes the output. You can put in here whatever you want. This is just, I use the text that was in the data sheet, but you could put here whatever you wanted to. It's one of the advantages in writing your own disassembler. You can put in here whatever you want and make it as readable as you want. If you want, you could put a sentence in here that explains what the instruction is doing. And then once it's done that, it breaks and it will go back round, and at the end of the switch it will use these two characters to move to the next line in the output file, and it then starts on the next instruction. Some instructions are multi-byte, so if it finds one of those, we'll scroll down, and whether they are multi-byte, whether it needs to read more data. So if we get one like this, it finds this instruction, outputs the data. It's a single byte instruction again, but it needs to represent the data in hex form, so there's a data value attached. So it reads the data value, and it wrote a small function to convert decimal to hex and put that into a buffer, and that's what it's doing here. It's just using the same function to convert the byte value it's read into a hex value, and it's outputting that in the file. Or sometimes it needs to merge two values that it's read. So if we look at an instruction like this is a call, then it's 2 bytes, but we need to output the destination address, and part of the destination address is in the first byte and part is in the second byte. So it has to calculate the address, and it does that, and then it represents that as a hex value. And again, it inserts any formatting information that it might need. Now you could of course simplify a lot of this. For example, this could be a single line. In fact, it could all be a single line, but that's the way it works all the way through. And again, with an instruction like this is all really one instruction that you can see on the screen at the moment. You could put this into a loop, but this is far faster. It's a much faster way of processing the file, which you'll see in a few seconds. So once we've got all the instructions in here, and we've got the way of handling each instruction, and all we have to do at the end of the switch, it is quite a long switch, obviously there are quite a few instructions in this device. So I go to the end, you can see that all we have to do at the end is create the new line. So we move to the next line in the file, and then we increment the line number. And the line number is just used for housekeeping. And that's it. The rest of it is error detection, and then right at the end we're just closing off the file handle and deleting the buffer that we created. If we don't do that, we'll get a memory leak in the program. And that's it. It's as simple as that. It doesn't take very long to do. What I will probably do, as I said, is make an initial run, so make it a two pass thing, and it's a very similar idea to this. It just looks for instructions where a jump occurs, and we'll probably just create a table of those, and then in this part of the code it will just look into that table, and if the instruction in the particular line that's being processed requires a label, then it will insert the label first. If the address that's been calculated is in the table, then it will convert that into a label as well. So a very simple disassembler. It seems to work very well, and the output it's giving is seems to be far more realistic, and it does seem to actually work, whereas the one I had from the disassembler I downloaded doesn't seem to work correctly. So we'll compile this, and the way it works is you get this small window, pick the file that we want to process, and then it generates an output file name, but you can type in whatever file name you want. Click on process file. That's now finished. You can see it's extremely efficient, and we can now open that file, and this is the output that we get. So the formatting is obviously entirely up to the disassembler. We can change that, but I kind of like this layout. As I said, I might make it a multi-pass, so what it would do in that case is it would keep a table of basically a symbol table of all the addresses that are in jump instructions or call instructions, and it would then replace this text with a label, and it would do the same thing with the line number. So it would do it would change this 0031 with a label, and then it would change the same address with a label as well. So the labeling you use is of course up to you, but you can also do it another way if it's a small file like this, and just do a find replace using Notepad. And it depends on how much use you're going to put the disassembler to. If it's going to be heavily used, then it's good to have multipass. If it's just a one-off thing, then there's no real value in doing that. But hopefully you found it interesting. It's going to be a useful tool, and as I said, the next thing I'll do is go through this and annotate this file, and from that point on we can start looking at the hardware and designing the new memory card for the Fluke.